In this lecture, you will learn about the different methods for calculating the quality of life index. The outdoor environment affects human beings differently. If it is too cold for the organism, that could cause frostbite, freezing, and other dangerous for the health issues. On the other hand, if it is too hot, the heat stress could become too high, and consequences such as heat stroke, fainting, or others could emerge. In either case, the outdoor environment could become deadly for humans. Climate change requires human individuals to adapt to current and future thermal conditions. The current research aims to study the risk of extreme heat and cold thermal stress on the Balkan Peninsula and some adjacent territories. For that purpose, we performed numerical simulations with the Regional Climate Model REG-CM4 for the period from 1975 to 2005. We studied the extreme thermal conditions in the cold and the warm seasons with two different biometeorological indexes. The first one describes how cold the human individual feels in low temperatures and windy environment. The second one describes how hot the human being feels in high temperatures and humid conditions. The simulation results for the influence of the current climate on human beings are demonstrated in the lecture. The heat stress for human beings is one of the most important problems in modern society. There is a lot of research work addressing that problem and the need for mitigation activities towards decreasing the harmful impacts on people. According to IPCC reports, the temperature is increasing at many locations in the world. At some places like the Mediterranean, the climate projections show that the changes in the future are towards drought and temperature increase on the surface. The heat index is defined as the temperature a human individual situated in a real environment would feel in a base environment with effective wind speed 2.5 meters per second, vapor pressure 1,600 pascals, barometric pressure 1,013 hectopascals, and zero extra radiation. It depends on the air temperature and relative humidity, and categorizes the thermal sensation according to the heat stress for the human organism. When the temperature and the relative humidity become very high, the evaporation from the human body starts to decrease, which could increase the core body temperature to dangerous levels. The heat index is applied for air temperatures above 26 degrees Celsius, and relative humidity above 40% shown on Table 1. For temperatures higher or equal to 20 degrees Celsius, we used an NCL algorithm for the heat index. For air temperatures lower than or equal to 4.4 degrees Celsius, we use the new wind chill index, or just WCI, which indicates the influence of cooling power of the wind on the thermal sensation in low air temperatures and wind speed equal or greater than 1.34 meters per second. The wind increases the convection from the human body, and when the temperatures are low enough, the human could feel surface or deep frostbite, hypothermia, or fall dead. It is categorized in 7 grades according to the sensation and the rate of skin freezing shown in Table 2. In order to evaluate some important temperature extreme events, we use 2 procedures developed in the Statistical and Regional Dynamic Downscaling of Extremes project for European regions. It has many objectives for the intercomparison of statistical and dynamic downscaling methods, the study of extreme events, and so on. One of its objectives was to develop a diagnostic software tool for calculating a standard set of extreme event statistics from daily temperature and precipitation data. 2 characteristics of that set are the heat wave duration and the cold wave duration. We studied the heat and cold waves for each season and for the whole year. To reflect the influence of the relative humidity and the wind speed over the heat wave day and cold wave day calculation, we replaced the temperature with the new wind chill index or the heat index if the conditions for the one or the other index were met. When the temperature was between 4.4 degrees Celsius and 20 degrees Celsius, the air temperature was used. The results showing the geographical distribution of the percentages of occurrence of the 2 heat index categories, caution and extreme caution in 3 seasons except for the winter are given in Figure 1. We can see that only 1 to 2% of the cases in the spring are with caution conditions in the northern part of the domain in Moldova, parts of Romania and Ukraine. There are no cases with extreme caution. The autumn also has a small number of caution cases. They are between 1 and 2% in the most northern and southeastern parts of the domain, 5 to 10% and even more in southwestern areas. Unlike the spring, there are places with 1 to 10% at the most southwestern parts of the domain. The summer is characterized by a large number of caution cases with a more complex distribution pattern. The caution cases are between 1 and 2% in parts of Pannonian Basin, Transylvanian Plateau, Tyrrhenian Sea, the coastal areas, and in some of the western parts of the Balkan Peninsula. The places with caution cases between 5 and 10% are located in the low terrain forms of the Balkan Peninsula, Adriatic Sea, Ukraine, and the most southern parts of Asia Minor. There are the southeastern parts of the domain, where the percentages at some locations exceed 30. The percentage of extreme caution cases at the eastern parts of the Balkan Peninsula and Ukraine are mostly between 1 and 5% of all cases, with some places between 5 and 10%. Some spots in the most southern parts of Asia Minor account for 1 to 20% extreme caution cases. Other parts of the domain have no extreme caution cases. It was interesting to study the biometeorological conditions under cold temperatures. We did that by the percentages of cases of the wind chill index, or WCI, categories for all seasons but the summer, as seen on Figure 2. We can see that the cases with wind chill from 0 degrees Celsius and below are mainly in the low risk and moderate risk categories. Most of them belong to the first of the aforementioned categories. The percentages of low-risk cases in the autumn are between 1 and 5% in the southern low-terrain forms and in the northern parts of the Black Sea, between 5 and 10% in Bulgaria and on the western Balkan Peninsula, and between 10 and 20% in Romania, Hungary, Ukraine, and Austria. There are locations with percentages above 20 in the most northern parts and in the Alps in particular. The low-risk category percentages in Asia Minor are from 1 to 20 and some places with 20 to 30. The middle and northern parts of Italy display percentages of low-risk cases between 2 and 5 to above 50 in the Alps. The percentages of moderate risk cases are mostly between 1 and 5 in the middle and northern areas of the domain, with 5 to 20, and even above 60 in the Carpathians and the Alps. Concerning the high-risk category, there is a place in the northwestern corner of the domain with percentages between 1 and 5. The percentages of low risk in the winter are above 20 in the land areas of the domain, and above 60 in the highest mountains. Only the coastal area and the adjacent territories are with low-risk cases below 20%. The percentage of moderate risk cases in the winter are mostly between 10 and 20% in Bulgaria, Serbia, Bosnia and Herzegovina, and Croatia. It is above 20% in Romania, Ukraine, and the Alps, and from 10 to 30% in Hungary. The percentage with moderate risk conditions in Italy is from 1 to 20 in the middle parts, to above 60% in the Alps. The winter high risk is between 1 to 5% in the most northern parts, and up to 30% in the Alps. The distribution of the low risk percentages in the spring is similar to that in the autumn. However, the percentages are higher since the same areas with 2 to 5% are now from 5 to 10%, others with latter percentages of wind chill index categories are already from 10 to 20%, and so on. The distribution of moderate risk category in the spring is more similar to the one in the autumn, but still with patterns pointed out in the previous sentence. Therefore, it appears that the springs from 1975 to 2004 are a bit colder than the autumns, in particular concerning the wind chill index between 0 degrees and -9 degrees Celsius, which is visible especially in the Asia Minor Peninsula. The objective of the present work is also to calculate the impact of air quality, known as AQ, on the quality of life of different scales. The impact of the AQ on quality of life is an issue of great social and economic importance. Evaluating this impact will provide a scientifically sound basis for developing effective short-term measures and long-term strategies to mitigate the harmful effects of air pollution on quality of life. Tropospheric ozone produces harmful effects to forests and crops, leading to a reduction of land carbon assimilation that consequently influences the land sink and the crop yield production. The European Union has defined an excess indicator for the protection of vegetation. The AOT40, or accumulated ozone exposure over a threshold of 40 ppb, or 80 micrograms per cubic meter for vegetation, is the accumulated excess of hourly ozone concentrations above 80 micrograms per cubic meter between 8 a.m. and 8 p.m. Central European Time, in the months of May, June, July, which means growth season. This indicator is designed for the protection of crops and semi-natural vegetation. The AOT40 quantifies only ozone exposure, i.e. not the effective ozone uptake by, and therefore damage caused to, vegetation. The European target value is 18,000 micrograms per cubic meter, for an hour averaged over 5 years. The long-term objective is 6,000 micrograms per cubic meter, for an hour. The European Union has defined an excess indicator for the protection of vegetation and forests. The AOT40 for forests, or accumulated ozone exposure over a threshold of 40 ppb, or 80 micrograms per cubic meter, is the accumulated excess of hourly ozone concentrations above 80 micrograms per cubic meter, between 8 a.m. and 8 p.m. said, Central European Time over the period April-September. This indicator quantifies only ozone exposure, which means it is not the effective ozone uptake by, and therefore damage caused to, vegetation. NOD 60, number of days with 8-hour average greater than 60 ppb, 120 microgram per cubic meter. If the limit of 60 ppb is exceeded at least once during the day is recorded as bad. People with asthmatic illness have problems on bad days, so it is advisable not to have days like this. But the reduction of all such days is too ambitious. The requirement is usually limited to a maximum of 25 bad days during the period April-September. The requirement is usually limited to a maximum of 25 bad days during the period April-September. Even this requirement is difficult to meet in many places. Phytotoxic ozone dose, known as POD, defined as the accumulated stomatal ozone flux over a threshold of Y, is considered an optimal metric to evaluate ozone effects on vegetation. POD is often computed through the Dozonese model, which includes species-specific parameterizations for the environmental response of stomatal conductance. However, the effect of soil water content on stomatal aperture is difficult to model on a regional scale and thus often ignored. Therefore, an index based on stomatal ozone uptake, or POD, which describes the amount of ozone entering into the leaves, would be more appropriate. Specifically, the POD metric considers the effects of multiple climatic factors, vegetation characteristics, and local and phenological inputs rather than the only atmospheric ozone concentration. For this reason, the use of POD in the ozone risk assessment for vegetation is becoming recommended.